Hello everyone and welcome to the video solution for Instruction 5 for Mechanics of Materials. This week we are covering stress transformations that were done in lectures 10 and covered in week 3.5. For this, in this problem we have a pressurized cylindrical vessel of a radius of 1.25 meters and a thickness of 0.015 meters. It is made out of steel and it is welded at a 45-degree seam indicated in the diagram above. Given that it is pressurized at 8 megapascals, we need to find the normal and the shear stresses acting at that 45-degree seam. The first thing we need to recognize is that a pressurized vessel has two types of stresses acting on it, the longitudinal and the hoop stress. We will first find the longitudinal stress. If we define our axis system to be x horizontally and y vertically, we know that the longitudinal stress acts in the positive x direction and is given in magnitude by PR over 2T. In this case, P is the internal pressure, R the radius of the cylinder, and T the thickness of the cylinder's skin. If we plug in the numbers, we obtain 8 times 10 to the 6th pascals times 1.25 meters divided by 2 times 0.015 meters. Therefore, we get that the longitudinal stress is equal to 333.3 megapascals. Similarly, we can find the hoop stress. The hoop stress is in the positive y direction, and the magnitude is given by PR over T. Comparing it to the formula for the longitudinal stress, we see that it is exactly twice as large as the longitudinal stress. As such, we can write it as 666.66 megapascals. To illustrate this stress state, we can draw a square which represents our surface. We have a vertical stress acting at 666 megapascals, and we have a horizontal stress acting at 333.33 megapascals. It is important to note that there are no shear stresses acting in this state. Our goal is to find out the normal and the shear stresses acting at the 45-degree seam as drawn here. To do this, we can draw a Mohr circle to find out more. Taking a look at the Mohr circle, we define the horizontal axis to be the normal stress given in megapascals, and we can define the vertical axis to be tau, the shear stress, also in megapascals. Now, seeing that we had two normal stresses and no shear stress, we can define our two principal stresses to be at point A, signified by sigma x, which is then given by 333 megapascals normal stress, 0 in shear stress, as well as point B, signified by 667 megapascals normal stress and 0 megapascals in shear stress. Now, we want to find the normal and the shear stress at a 45-degree rotation. Here we have to identify that any rotation made in the physical world is equal to twice that angle in a Mohr circle. As such, if we had a 45-degree rotation at the seam, we therefore look at a 90-degree rotation at the Mohr circle, resulting in point C. Now, at point C, we know that the normal stress will be equal to the average shear stress of the Mohr circle, as well as the average normal stress, as well as the shear stress will be equal to, in magnitude, the radius of the Mohr circle. Now, to find the average shear stress, we can simply take the average of the two principal stresses. This would be sigma x and sigma y divided by 2. Sigma x, of course, being 333 megapascals, and sigma y being 666.66 megapascals. Divided by 2, we obtain the sigma average, the average normal stress, is equal to 500 megapascals. To find tau at this plane, we find that it is equal to negative radius as it acts clockwise. To find negative radius, we can simply take the average normal stress minus the higher principal stress, which is 666 megapascals, to obtain a shear stress of negative 167 megapascals. As such, we have now found the normal of the shear stress acting at the 45-degree seam. If you have any further questions on this problem, please feel free to join the instruction sessions on Thursday and Friday to ask any more questions to our TAs. Thank you for listening.